Hello there!
Hello there.
In this video, we will learn these things about the Chain Chomper. Its speed, its power.
Damn, son.
How much energy his thrusts can generate. And trust me, a lot more. Before anything happens, if you haven't watched my other video on the Chain Chomper, go do that now. I'm not asking, I'm ordering you.
You're a fake and a fraud.
If you have watched it, let's begin, shall we? We can calculate the power of this menace in many different ways, depending on what we mean when we say the word power. I think that we all want to know questions like, if this thing hit a car, how fast and at what speed would the car fly in the other direction? In that case, we will need to calculate its momentum, which equals its mass times its speed. We know the mass since we calculated it in the last video, so before we calculate its momentum, we first need to calculate its speed. In order to calculate its speed, we need to know the distance it travels and at what time it travels that specific distance. We will not be calculating at what speed he thrusts against us, cause that's just cringe. We will calculate the distance in this video when he lets himself loose against the iron fence.
Because
Here, he travels a greater distance at insanely fast time. Let's see at what time he travels this distance.
0,
He's still there.
1,
Already left.
0.51,
He leaves.
13,
He already at the gate, which we can tell since his chain has gotten tighter.
11, 12.
But we don't know for sure.
11.5,
Is the most realistic answer. So he travels this distance in less than 1/5 of a second. The last thing we need is the distance it travels. First we need some measurements about some things, so we can compare some distance. This wall here looks good, since here we have a very nice triangle. We can calculate this long side by knowing this angle and the height of this side. According to this protractor, the angle here is 20 degrees, but it's actually around 19.75 degrees. Apparently, it likes to round up. I don't. We then compare the height of this wall to the Chain Chomper's height, which we calculated in my last video. The Chomper's height in this picture is 21%, and the height of the big wall is 32.55%. We divide these two numbers, and we get 1.55. That is exactly the height of Mario. What the f... So by multiplying 1.55 with the height of the Chomper, we get that this wall is around 8.773 meters high. We then use this formula to figure out the length of this side. We put in the angle and the height of the wall, and get that this side is 24.4 meters. Now when we know the measurement for this side, we can go ahead and drown ourselves in tar. Now we need to use both of our brain cells. We need to know from where the Chomp started his mega thrust against the metal prison. We can see that just before his thrust, he made a small jump from this position and landed on us. Where is us? He is closer to the muddy, moist ground than he is closer to the stub. Then he jumps, not straight, nor gay, but with a slight angle. I rewatched the clip and tried to figure out where he landed. I ran around for at least 45 minutes to gather the most accurate position. This is the final and most accurate footage. By running from this angle, in a straight line, I ended up here on the calculated wall. As we saw earlier, he jumped with a slight angle. By moving a bit to the left here, we do not only get a more accurate position on where he was, but as you can see, Mario is as tall as the wall on this specific position. I think you know what that means. We will redo the exact same calculation as last time, but with 1.55 meters, and we get 4.3 meters. Our measurements start to add up here. If we look closely on the movement when the Chomper makes his mega thrust, we can see that he hit the middle of the iron fence, hence being at a slight angle. What it looks like, the Chomper is not adjacent to the wall. He dashed from around this position to this position, making the distance he traveled parallel to the wall, since the wall isn't straight either. I was extremely happy when I realized this, since then I know that the numbers will be very accurate. The distance the Chomper traveled horizontally is these 24 meters minus these 4.3 meters, which gives us 20.1 meters. I mentioned horizontally, since he through the process even gained some airtime. He does not travel this distance, he travels this. Let's check the height he gains through my edit program. The height of the jumper in this picture is 23% and the jump is 10.3%. So if 23% equals 5.66 meters, then by dividing the scales times the jumper's height will tell us how high up he is. The answer is 2.5 meters. We will use Pythagorean theorem to know what distance he traveled. We put in the numbers and we get 20.27. Such great difference. Wow! Almost 0.60 meters in difference. Imagine if we didn't calculate that. People would have
died.
Now we have everything we need to calculate its speed. We put in our numbers 20.27 and 0.18 and round it to the closest whole number, and we get 111 meters per second or 398 kilometers per hour. For a sphere dog made out of iron, I'd say it's kinda fast. If you're driving 130 kilometers an hour on the highway and you think you go fast, this boy goes 3 times as fast. Now, let's see how much power this boy has. The momentum equals its mass times the velocity. And we get... But wait! We know the weight of the jumper, but not his chain, which he thrusts with. Let's calculate his chain. Real quick scope here. Now that we have the weight of the 4 balls that his chain consists of, we can go ahead and add those to the weight of the jumper to get a total of 764 tons. Let's figure out his power. We put in the mass times the velocity and get 84 million kgs times meter second. So what does this number say? Let's take the car example here under these circumstances. The car stands still and is unbreakable. It happens on regular asphalt and the roll friction coefficient is 0.01. Forces applied to the car are viewed as constants. The weight of a Honda Civic 2001 is 1,167 kgs. But with Joe inside with all his ketamine, it would have an estimate weight of 1.5 tons. Now we let our dog out to thrust this car. What would happen if all of the impulse power would transfer to the car? We use the same formula, momentum equals mass times the velocity. To know what speed Yoda and his car gets after being hit with the mass of destruction, we simply divide the momentum of the jumper with the mass of the car. And we get 56,330 meters per second, or beyond 200,000 kilometers per hour. In real life, the car would just explode into oblivion and would not look like a car anymore. But how far would the car travel?
Warning, next scene contains material of a man using his formula book instead of using Google. Viewer discretion is advised.
We will first use this formula to calculate the friction. We will then calculate the energy that this thrust generates. We then use the finisher and divide our thrust energy with the friction to get the distance it travels. Under these circumstances, the car would roll 16 kilometers times 1 million. It would for real roll 16 millions of kilometers, or for all your eagles out there, 10 millions of miles. If you by any chance wonder how long the distance around the Earth is, I can tell you that it's around 40,000 kilometers. So that would mean that it would travel around the world 403 times, with a starting speed of over 200,000 kilometers an hour, which by the way is 164 times the speed of sound, before the car would stop. Imagine you, in an alternate reality, minding your own business, driving to work. You stop at a traffic light, and then, from nowhere, this dog thrusts you and your car, so you travel 403.9 times the Earth. Like it wasn't enough with the 403 laps. No, you travel another 90% of Earth. So now you are 4,000 kilometers away from home. Dinner's gonna be cold, and you probably missed your daughter's dance lessons. Probably. Let his power sink in for a few seconds. We can make it a bit more realistic by adding some more ketamine to the weight of by adding air resistance. I found this formula to calculate the air resistance on a website from NASA, since it wasn't included in my formula book. So the data we need is 1. The drag coefficient. The drag coefficient for a Honda Civic is around 0.27 times half of its air density. On another NASA page we found the air density under certain circumstances times the velocity squared times the reference area. The reference area for a Honda Civic is 1.795 times 1.440. And that's it. We put in the numbers and we get 1.35 billion Newton. Now we have the air resistance. We repeat the same thing and divide the energy the car got by our new friction plus the old 147.3 and we get 1760 meters. That's how much difference the air resistance makes, since the resistance gets greater the higher speed it has, from around 404 times the whole world to 1760 meters. These calculations on how far the car would travel are correct if we view the air resistance as a constant force. As stated, the air resistance grows the higher speed the car has and gets lower the slower the car travels. It would travel 1760 meters if the air resistance had the same high force from start to finish, which might be true in some other universe, but not in ours. But if it was true, it would have traveled these 1760 meters in around 0.063 seconds. But if we want the numbers to be a bit more closer to the truth, we can calculate the air resistance as a linear force instead of a constant. 100% of force is applied when the speed is 100%, 0% of force applied when the car has 0% speed. 1.35 billion Newton at the start and 0 at the end. We divide it by 2, which doubles the distance it travels, if we want it as realistic as we can. We can dive one step further down the math iceberg and view the force as accelerating, which we achieve with numeric integration. It might sound scary, trust me, it's not. Instead of calculating the whole distance in one big step, we split the time it takes for the car to stop into many small steps and calculate what happens in each one. This is how numeric integration works. Since it travels very fast in very short time, we want to pick very small time intervals. In each step, we calculate the air resistance based on the current speed. We then use that speed to calculate the acceleration. We update the speed and see how far the car travels in that short time. We do this over and over again until the speed reaches 0, which means that the car has stopped. The total distance the car has traveled is the sum of all these small steps. The smaller time intervals we take, the more accurate the answer will be. So let's take 0.0001 seconds intervals. Calculating this by hand would be too time-consuming for the immortals.
Good thing I'm immortal.
This Python script will tell us how far the car would travel. So the car would travel 28 kilometers for almost 5 minutes. So 404 laps around the world with roll friction. 1760 meters when we added air resistance. 3,521 meters with average air resistance. And 28 kilometers when the air resistance decreases with speed. Instead of Chomper thrusting the car, let's say the car instead got hit by Yoda, diced to the socks. Then the car might have a start speed of 100 km per hour. If so, then the car would have rolled around 1,215 meters in around 87.5 seconds, without decreasing air resistance. And 2,065 meters in around 3 minutes if we added this decreasing air resistance. But does a car really roll 2065 meters if I stop gassing at 100 km per hour? Probably not, because the car has its own resistances within itself, like engine braking and a bunch of different mechanical frictions. And the ground you drive on probably isn't perfect nor 100% flat either. Very nice to know. And finally, what does the energy of one of these Chomper thrusts compare to? To calculate the energy of the Chomper in this dash, we simply use the same formula we earlier used to calculate the energy. But this time, we use the weight and speed of the Chomper instead of the car. We put in his mass and speed, which gives us 4.7 billion joule. That is equal to 5 lightning strikes at the same time, or around 1.1 million calories. If you eat 2000 calories a day, it would last you 558 days. That's more than 1.5 years from just one thrust, or 1.1 ton of TNT. That's enough power to end this video.
Like, subscribe, comment, we'll calculate next time, we will.